Morning, grade 12s. So I'm just going to make a quick video here just explaining how to use Desmos to find an exponential model. So I'm going to first assume that you all know how to put in the table on Desmos. We already done that a couple times, so that should be familiar to everyone. So again, I'm just going to quickly review this, go to the plus sign and then click table, and then you start entering your data. So if you want to create an exponential model, all you're going to be doing is typing in a new command. And again, this is all in the handout as well. But as I mentioned already, I'm just making a quick video just so you can actually see it yourself step by step. So how I enter this in is I go to my second line. Make sure you write it on the second line here. You're going to write Y1. Just like before, and then you're going to go look for the squiggly line, and I'm actually going to show you on the keyboard because that's what most of you are going to see if you're using a phone. So you go to where it says ABC, and then you're going to see all these different characters. You're going to write approximately equal to, and then you're going to write A, B, and this might be the bit of a new one. It's going to be AB to the power of X1. So you have to go back to the numbers here. So go back to 1, 2, 3. And you're going to be looking for this symbol here. If you put in this square here, it's going to give you something completely different. That's actually quadratic. You want it to be exponential, which means that the variable is going to be in the exponent. So you're going to click on this little button here that says a to the power of b. So click on this. And when you do that, it automatically creates an exponent for you. And here you're going to type in x1, just like before. And then when you're done, just move your cursor so that it's not, you don't keep writing on the exponent, okay? You always have to move the cursor back. And then you can check how strong of a correlation it was. I did this on purpose. It was a relatively strong correlation. I switched numbers a little bit. If you noticed, if it had been 2, 4, 8, 16, 32, it would have been perfect. I changed the number slightly so it wasn't perfect. So you kind of see how an exponential model works. So we found an exponential relation that does go through most of these points, right? We can see here that it's pretty accurate there. And actually, to be specific, its correlation coefficient is 0.9999, right? So it's pretty good. So that's how we do. That's how we draw an exponential model on Desmos. The second thing I want to show you is how to use Desmos to actually graph different exponential functions. So what if they give you the equation and then you want to see what the graph looks like? So I'm just going to get rid of these for now. Actually, just to make some space, I'll exit them out. And let's say I type in, okay, so I'm just going to make this up. Let's say that we have an exponential function that is 2 times 4 to the power of x. So first, the 2 is going to be our a value. The b is how much it's increasing by. So in this case, I'll make it 4. That'll be the multiplicative factor. So that basically means each time I increase my x coordinate by 1, I'm basically multiplying the y values by 4. That's what I'm saying there. And now I'm going to raise the 4 to the power of x to create an exponential function. So to do that, I simply click on this button right here, a to the power of b. And then I press X, and then I'm done. That's how you graph any function on Desmos. It's pretty easy to use. And then once you graph it, you can see a lot of different components of this relation here. So we can obviously see here, hope everyone can kind of identify this, that we have our A value right here. And again, this is going back to the equation for an exponential function. Our A value is our y-intercept, which is 2. That's where we start. And our b value, this one right here, is our multiplicative factor. That's basically what we're increasing by each time. And it should kind of make sense because if we go from, let's say that we go from and again, it's going up by 2, so it's a little bit hard for you to see maybe. Let me just change the scale so it actually shows the 1. I don't know why the sides always go up by 2. Okay, so here we have, now we can see this a bit more clearly. If we're going from 2 all the way up to 8, sorry, let me throw this back on, all the way up to 8. And again, why am I comparing these two? Because I am trying to see how much the graph changes by as x changes by 1. So right now that I've changed by 1, I went from 2 all the way up to 8. And so I can see here that it has been multiplied, the y value has been multiplied by 4. And so essentially we multiply by 4 every single time that we move an x value by 1. So that's our multiplicative factor in that case. So I hope that kind of makes sense. Just wanted to show you a couple things on Desmos and how that works. And for the other questions, I believe that there are some homework questions that you are doing today where it actually makes it a little bit more difficult. It says which model is better. So if you're given a question where it's asking you which model is most appropriate, linear, quadratic, or exponential, what you need to do here is simply put in your information on the table. So I'm just going to make this up. 1, 2, 2, 3, 4. I'm going to give a couple data points here. So we have 2, 4.5, 8.8. I'll make this 17. I'll make the last one 30. I'll just switch it up a little bit. So it almost looks like it could be exponential. It doesn't look linear because you can see here it doesn't lie perfectly on a straight line. But let's say that they ask you, okay, what are some different, which model is most accurate? What you would actually have to do is test this out on several models. So we'll try out the linear model. So we write y1 is approximately equal to mx1 plus b. And I think everyone's okay with that part. And we can see here that there is a line of best fit, but it's not a great line of best fit. It doesn't have a strong correlation coefficient, but sorry, it's relatively strong, but I wouldn't say it's the best. So let's try out the quadratic one. So the quadratic one is going to be y1 is approximately equal to, and I always find this is the hardest one to write, ax1. And then we're going to go to where it says the square button there. And then don't forget to move the cursor. If it is at the top, you don't want it to continue on the exponent there. And then we're going to write plus bx1 plus c. And we press enter, and then we're done. So we can see here, comparing the two of them, the r squared value is a little stronger in the second example. And it seems like, if we look at, let's just compare them directly one by one. The line, a couple points are a little bit off. It's not necessarily very close to it. With the quadratic one, let's see what it looks like. Looks a little bit better. It seems pretty close to all the points there. So already looking at the quadratic one, it seems like it's pretty good. And to zoom in, zoom out, all you have to do is kind of scroll in, scroll out, or you can click on these buttons there. And then let's just try out the last one, exponential model. So we have y1 is approximately equal to a, b, and then we're just gonna use this button to create the exponent, and then it gives us x1, and then we're done. Then we just move the cursor, and we can see here that the last one is even more accurate in comparison. So actually, let's see what it looks like. Yeah, that's definitely a lot stronger. Actually, they're pretty equally strong, to be honest with you, in this case. So it seems like the quadratic or the exponential model would work. And again, I made this example up, so it's obviously not the best example, but you kind of can see how we can find different models for our graph there. So you essentially want to pick the model that gives you the strongest correlation coefficient there. So I hope that makes sense, and I hope that kind of explains how we find different exponential, linear, and quadratic models. All right, best of luck.